Ever heard of a gravistar? It's this super cool alternative to black holes. Picture this. Instead of collapsing into a singularity, a gravistar has a core filled with dark energy, wrapped in a thin shell of matter. From the outside, it looks just like a black hole, but it doesn't have an event horizon. It's like a black hole's cousin.
For centuries, we believed we had a handle on the stars. They are born, they shine, and they die, a grand but predictable life cycle. But hidden deep within the equations of modern physics, another kind of star has been lurking. A star that doesn't shine, has no core, and isn't even made of normal matter. Some physicists theorize they are completely hollow, containing only a vacuum, the very emptiness we assume is nothing, yet which holds the universe's most immense energy. These objects go by many names: strange stars, vacuum stars, and most notably, gravastars, short for gravitational vacuum stars. Sounds like science fiction. Perhaps, but the gravastar was born from the most rigorous equations of relativity and quantum mechanics. And if it's real, our entire understanding of the black hole, the ultimate symbol of cosmic mystery, may have to be rewritten. Before we get to that wild theory, let's start with something familiar. Our nearest star, the Sun. The Sun is the perfect example of how the universe operates its giant fusion reactors. From Earth, it looks like a solid, brilliant disk. But if you could get closer, you'd realize it has no surface at all. The Sun is a raging sea of plasma, a place where matter is superheated into a violent, swirling storm, and where gravity and radiation are locked in a cosmic tug-of-war. Gravity tries to pull everything inward, wanting to crush the Sun under its own weight. But deep in the core, nuclear fusion reactions are constantly firing, turning hydrogen into helium and unleashing colossal energy in the form of light. That energy creates an outward force called radiation pressure, which perfectly balances gravity's inward pull. This delicate equilibrium is what allows the Sun, and every other star, to remain stable for billions of years. But what happens when the fuel runs out? When the radiation pressure weakens, the Sun will begin to contract, and its temperature will skyrocket. The core will become hot enough to start burning helium, kicking off a final, brilliant phase as the Sun swells into a red giant, growing so large it could swallow the Earth. But even this stage is temporary. Once all the fuel is spent, the reactions will cease, and gravity will finally win. The Sun will collapse, shrinking down to the size of our own planet. But it won't collapse forever, as its atoms are squeezed impossibly tight. The quantum world steps in. The electrons orbiting the atomic nuclei refuse to be crushed into the same space. This fundamental rule of quantum mechanics creates a new kind of outward force called electron degeneracy pressure. It's this pressure that will halt the Sun's collapse, leaving it as a white dwarf, a small, dense, slowly cooling ember. That star no longer burns, but it stands as a testament to the fine balance between matter and energy. Which leads to the next question: if a normal star like our Sun is bound by these physical limits, what happens to stars that are bigger, heavier, and far more extreme? Stars much more massive than the Sun don't go out quietly. They are born and die in explosions that can shake an entire galaxy. When the fuel in their core is exhausted, nothing can stand against the crushing force of gravity. The star begins to collapse, so rapidly that its immense mass implodes in a matter of seconds. The core becomes so dense that the particles within are squeezed together until there's no space left between them. If you could bring a thimbleful of this material back to Earth, it would weigh as much as a mountain. This is a neutron star, a tiny remnant, perhaps only a dozen miles across, yet containing the mass of our Sun, a marble that outweighs anything you can imagine. A neutron star proves that the universe can compress matter to an insane degree without it breaking. But even it has a limit. If the original star was massive enough 2 or 3 times the mass of the Sun, no force is strong enough to stop the collapse. Gravity is no longer just pulling, it's devouring. The star falls into itself with no point of return. Light, the fastest thing in the universe, cannot escape. Anything that crosses an invisible boundary, the event horizon, is lost forever from our known universe. What remains is a black hole. From the outside, It is a pit of absolute nothingness. Light bends, time stretches, and space itself warps around it like a fabric being pulled down. When you look at the first image of the M87N black hole, that ring of fiery orange light surrounding a perfect void, you are seeing that very boundary, the last orbit of light before it's swallowed whole. For decades, scientists believed a black hole was the end of the line, a place where everything is crushed into nothingness. But then, a question emerged. What if it's not nothingness inside? What if something else exists in there, a more stable, ordered structure? That question opened a new path. Because if a black hole isn't the final stop, then perhaps something else exists between a star and a black hole, an object we've never seen, but which physics allows. A strange star, sitting on the very edge of light and darkness. When the black hole was discovered, it became the undisputed king of the cosmos. Nothing could be denser, smaller, or more powerful. But physics, as always, refuses to accept the word impossible. Scientists began to wonder, what if a star wasn't made of normal matter? If hypothetical forms of exotic matter could generate pressures even greater than neutron degeneracy pressure? Could new types of stars exist? You might think we could just continue the pattern we saw before. Stars could get smaller and denser than neutron stars, as long as they were supported by a greater pressure. You might think the only limit to how small these stars could get is the point of no return, where they become black holes. That point of no return is when a star becomes smaller than its own Schwarzschild radius. This is almost true, but not quite. Instead, physicist Hans Adolf Buchdahl proved in 1959 that a star made of any kind of realistic matter, with positive energy density and pressure, can't be smaller than 98ths of its Schwarzschild radius. It may not sound like a big difference, but that 98ths factor means any realistic star has to be significantly larger than a black hole, making it much easier to tell them apart. That's when physicists started asking about the stars that Buchdahl would have called less realistic. What if, for instance, a star was made of a material that allowed for negative pressure in some regions and positive in others? Then, Buchdahl's limit wouldn't apply, and that star could be smaller than 98ths of a Schwarzschild radius, in fact. It could be almost exactly the size of a black hole of the same mass. As a side note, theoretical stars like these that can mimic the appearance of a black hole have become a nuisance for astrophysicists, because now every time they detect something they think is a black hole, they can't just say they detected a black hole. They have to confirm that it's a black hole, or a black hole mimicking ultra-compact object, even though in their hearts most of them are pretty sure it's a black hole. But to the point, what would these strange, negative pressure stars even look like? The answer turns out to be even weirder than you might guess. Tolman, Oppenheimer, and Volkov worked out an equation back in the 1930s that describes how the pressure of a stable star changes as you move outward from its center. Today, it's just called the TOV equation for short. If the center of a star has a significant negative pressure, which creates a gravitational pull instead of a push, the TOV equation says that this star can only be stable and in equilibrium with its own gravity if the pressure does something truly bizarre. First, the pressure has to blow up to negative infinity somewhere inside the star. Then, it has to flip signs to positive infinity and fall off from there until it reaches zero pressure, which marks the outer surface of the star. The more negative the central pressure is, the sooner it will go to infinity. On the other hand, the less negative the central pressure is, the further out that surface of infinite pressure gets pushed. It turns out there's an interesting limit where the pressure stays finite, right up to the edge of the star. That happens when the pressure at the center is exactly equal and opposite to the energy density there. In this special case, the TOV equation says that the pressure and energy density stay constant, equal, and opposite throughout the entire volume of the star, right up to the surface. If you've watched some of our other content, this might ring a bell. A constant. Positive energy density, combined with a constant. Negative pressure. This doesn't sound like any star we've seen before, but it is starting to sound like a mysterious component of our universe, dark energy. And because the pressure and energy density in a gravastar are equal in magnitude, it's not just any kind of dark energy, it's precisely the signature of vacuum energy. That's why this particular strange star is known as a gravitational vacuum star, or gravastar for short. Inside a gravastar, there is effectively no gravity, because the positive energy and negative pressure create mutually canceling gravitational pulls and pushes, respectively. And because the pressure inside a gravastar is constant, there's no pressure gradient to create a push in one direction or the other. This means that if you found yourself inside a gravastar, you wouldn't be pulled in or pushed out, you could float freely, just like in a true vacuum. Another interesting feature of stars with negative pressure is that the closer they are to the special limit of a gravastar, which, if you remember, is when the surface of infinite pressure is pushed out to the edge of the star, the closer their size is to a black hole of the same mass. This raises two key questions that have received a lot of attention from physicists recently. First, how can we tell whether the ultra-compact objects that astronomers observe in mergers and at the centers of large galaxies are black holes or just strange stars of a similar size? And second, if gravastars are real and are scattered throughout the universe, could they be the dark energy that has been accelerating the universe for the past 5 billion years? To answer the first question, physicists rely on the key distinction between a black hole and any other compact object, the existence of an event horizon. You see? The defining feature of a black hole is that nothing that falls inside or even touches the surface of a black hole can ever get back out. On the other hand, if a strange star is even slightly larger than a Schwarzschild radius, it won't have an event horizon, and it can emit information outward in the form of light. Not only that, but objects without event horizons may have different signatures in their gravitational wave emissions than black holes do during a merger. This allows us to tell them apart by measuring and analyzing those gravitational waves using observatories like LIGO. But even with this battery of tests, it turns out that stars that are small and dense enough are still difficult to distinguish from black holes. To date, the best we can do is say that the radii of the black hole candidates we see in the universe are at least approximately equal to their Schwarzschild radii in some cases. That's just a rough estimate, but in other cases, we have the radius pinned down to 40 decimal places. As for the second question about dark energy, that's where things get really heated. In early 2023, an analysis led by physicists at the University of Hawaii found that astronomical observations of supermassive black holes show them growing in mass over time, at exactly the rate that dark energy would be expected to increase over time due to the expansion of the universe. They came to the seemingly inescapable conclusion that black holes must be made of dark energy, and that they are in fact more like gravastars than conventional black holes with an infinite density singularity at their center. This conclusion is highly contested. Astronomers argue that the analysis of the observational data wasn't quite right, and theoretical physicists argue that the expansion of the universe shouldn't have anything to do with the growth of black holes in any case. So while the idea that dark energy could exist in the form of gravastars is an intriguing one, it seems that the scientific community won't be convinced unless it's backed up simultaneously by better data and more convincing theoretical models. But where do you stand in this debate if it walks like a black hole and talks like a black hole? Should we just call it a black hole? Or should we entertain the possibility that black holes are really secret treasure troves of dark energy? Share your thoughts and questions in the comments.